When you spin a bare steel shaft at extreme speeds inside a fixed housing, metal-on-metal friction generates enough heat to weld the components together. To prevent this, engineers have to manage the physical stress of that rotation, which presents itself as two distinct, destructive load forces. The first is radial load, any force acting perpendicular to the shaft, like the weight of a heavy gear pulling downward. The second is axial load, or thrust load, which runs parallel to the shaft, pushing directly against the end of the rotating assembly. Because these force vectors push in completely different directions, specific bearing architectures are required to resolve them. We are going to analyze exactly how these architectures work, tracing the evolution from simple fluid sliding bush bearings to highly engineered mechanical rolling elements. Then, we will simulate how industrial load specifications dictate their physical limits and review the strict maintenance protocols required to keep them intact. Without precise geometric interventions, the combination of radial and axial stresses will cause high-speed mechanical assemblies to destroy themselves in seconds. The most basic solution to shaft friction relies on fluid dynamics rather than internal moving parts, the bush bearing. This technical diagram of a pedestal bush bearing shows the two primary structural components, a fixed outer housing and an inner shell where the shaft rests. Notice the reservoir at the top. This introduces a steady supply of external lubrication down into the gap. As the shaft rotates, it drags this lubricating oil underneath itself, creating a hydrodynamic wedge. The shaft physically lifts off the metal lining and floats entirely on a microscopic film of oil. Because there are no internal mechanisms separating the metals, this is categorized as a sliding contact bearing. This lack of moving parts makes bush bearings exceptionally quiet and excellent at dampening vibration. You will frequently find them supporting oscillating or reciprocating shafts. But relying purely on fluid pressure has limits. While sliding contact handles basic friction well, its load capacity is structurally limited compared to mechanical rolling elements. To resolve higher physical forces, engineers replace fluid sliding with mechanical rolling elements. This cutaway shows a deep groove ball bearing, the standard geometric architecture used across industries for high radial capacity. Instead of relying on fluid, the inner and outer rings are separated by spherical rolling elements nested tightly within deep machined raceways. When perpendicular force is applied, deep grooves channel the stress into the spheres, smoothly distributing the load. But if a parallel axial load is introduced, the geometry fails. The balls jam against the steep sidewalls, creating friction that will shatter the bearing. To handle both forces at once, the internal geometry must be physically altered, creating the angular contact ball bearing. By redesigning the rings with an asymmetrical shift, engineers create a specific contact angle between 15 and 40 degrees. Now, when combined radial and axial loads hit the assembly, the intersecting vectors channel cleanly through that angled line of contact, eliminating the pinching entirely. This specific geometric adaptation is used for complex load environments, from aircraft control frames to automotive spindles. The shift from deep groove to angular contact illustrates a strict mechanical rule. The physical shape of the bearing's interior dictates exactly which direction of force it can survive. But how do engineers support industrial forces that completely exceed the structural crushing limits of a standard steel sphere? The solution is to abandon the sphere entirely. Engineers replace them with cylindrical rollers, introducing the concept of line contact. A sphere only touches a track at a single point. A cylinder contacts the track across a wide rectangular line. This expanded footprint physically disperses the pressure, granting massive increases in radial rigidity and impact resistance. When those extreme loads are coming from multiple directions at once, the design evolves into the tapered roller bearing. By using coned raceways and angled cylindrical rollers, this architecture prevents heavy shaft deflection in systems like aviation cargo and heavy agricultural machinery. There is, however, one final force profile. Some mechanisms experience almost no perpendicular stress, dealing entirely with aggressive parallel forces. This dimensional schematic shows a ball thrust bearing, built strictly to resolve axial loads. Because its geometry is oriented for end-to-end compression, engineers must match exact dimensional specifications, the outside diameter, the bore, and the overall width, to the housing. You will find thrust architectures anywhere high axial compression occurs, such as an automotive clutch throwout mechanism or the rotating mast of a heavy radio antenna. By utilizing line contact rollers and specialized thrust plates, engineers trade the high-speed versatility of ball bearings for the structural rigidity required in high-load industrial environments. Selecting the correct geometric shape is only the first step. That geometry is useless if the applied forces exceed the mathematical limits of the metal itself. To prevent material failure, engineers verify 3 core operating specifications provided by the manufacturer: dynamic radial load, dynamic axial load, and rated speed. Let's evaluate a tapered roller bearing against a demanding set of requirements. As long as the physical RPMs and vector forces stay within the mathematical thresholds, the unit operates safely, reaching its intended lifespan. But if you exceed those ratings, the internal pressures will physically overwhelm the steel. The rollers and raceways suffer microscopic stress fractures, leading directly to metaflaking. A bearing's actual operating life depends on two final variables: environmental maintenance and chemical lubrication. To prevent friction damage, bearings require either oil or grease, and each serves distinct operational functions based on speed and temperature. High-speed applications generate massive excess friction, and they require a constant bath of circulating oil to actively carry that destructive heat away. Slower, sealed units rely on packed grease, which requires no replenishment and acts as a physical barrier against dirt. Even with perfect lubrication, the physical act of mounting a bearing can destroy it if strict handling protocols are ignored. Unmounting or seating a bearing requires specialized tools, like this manual arbor press. This ensures pressure is applied with perfect evenness, preventing distortion. The components are so sensitive that bare hands can be fatal. Perspiration leaves trace moisture on the steel, causing rapid rust and corrosive pitting. Brilliant mechanical engineering is instantly nullified if exact installation procedures and lubrication maps aren't strictly followed on the shop floor. The core engineering challenge of any rotating assembly is a delicate balancing act, resolving extreme friction while supporting multi-directional force vectors. We saw how the fluid dynamics of a bush bearing provide a foundational, low-vibration sliding contact solution for specific systems. When forces escalate, deep groove ball bearings absorb radial loads, while angular contact units manage both radial and axial stress. And when forces become punishing, cylindrical and tapered rollers survive heavy impacts, leaving thrust bearings to handle pure axial loads. Achieving mechanical efficiency requires precisely matching dynamic load data to specialized mechanical geometries. And it requires recognizing that even the perfect bearing requires rigorous installation protocols and environmental lubrication to survive its operating lifespan. Which brings us to a final computational question. Now that we understand the physical limits and geometric shapes of these components, how do engineers mathematically predict the exact timeline of a bearing's failure? To master the mechanics of heavy machinery, your next step is to investigate the exact mathematical formulas behind calculating rolling element fatigue life.
Thanks for watching. Please visit the channel for more content. Don't forget to subscribe, like if helpful, and comment if something is wrong.